coming to the presentation. Again, this is call number 99. And we're very excited. We have Dr. Marty Boyd, which is the chief engineer and co-founder of Vector Atomics, where he led the timekeeping team and the clock commercialization effort. Marty has 20 plus years of industry and academic experience, resulting in 30 plus publications and patents in atomic clocks, inertial sensors, and supporting laser and electronics technologies. Marty's PhD research was in Gila with the University of Colorado with Professor Yoon Yi. His group, including development of one of the world's first ultra-high performance optical lattice clocks. So today's presentation is about real-world optical timekeeping. And again, please mute your microphone so we'll not have any interruptions. And with no further ado, Marty, the floor is yours.
Okay, great. Thanks for the nice introduction. I'm excited to be here to talk to you about what we've been working on in timing at Vector Atomic.
Nice.
I guess I'll say for the real world optical timekeeping title, I'll let the audience decide if that should have a question mark. I think it should have an exclamation point, but we'll let the readers chime in at the end. Okay, just a little bit about Vector Atomic. We're a small startup in the Bay Area, out in Pleasanton. We're a little over 50 people now as of this month, so that's exciting. And we're a little bit different than most startups in the area. We're funded and bootstrapped through competitive grants and R&D contracts with the government mostly. And so we're sort of our own entity without any outside investment. And we've been really focused on, since the get-go, we've been focused on operationalizing some exciting atomic technology for PNT applications, clocks, and inertial sensors, and how to use those. And so you'll hear a lot about the clocks and optical sync modules shown there in the left two panels today, but I also wanted to call out our teams working on the gravimeters and gyroscopes. Those are really nice devices. The gravimeter has gone out to sea many times for navigation applications and is state-of-the-art in its form factor. The gyroscope has been delivered for use in space. So pretty cool stuff going on here if you ever want to visit. So the little flashback to the first time you heard from us in the seminar number 59, Jamil gave a talk that in a way was our coming out of the shadows for all this work. So that was really the first time we showed in a public meeting, what we've been working on with optical clocks and their use at sea, as well as how to distribute optical timing around the world with our sync modules. So that was a good experience. We met a lot of people through the seminar and made some good contacts and learned a lot about how, what people might want from this new technology. And it's there's some good symmetry here. The early results you saw live back in November 22 got published today in Nature, so the team here is pretty excited. And now I don't have to go through the gory details. You can go read pages and pages from John's nice paper about how we did that mission and why it's useful. And I'll say for those of you who already read the preprint version, there John added some nice analysis on long-term drift rates and how we managed pulling out the data from the 3 clock comparison. So definitely recommend taking a look. Might be more interesting than what I'm saying, but hopefully I'm saying some cool stuff too. So maybe wait an hour, but there you go. Hope you enjoy it. So why are we all about optical at Vector Atomic? Well, it's easy to kind of think about it starting from the microwave situation. Many of you are probably clock makers or clock users, and so for some this is review, but generally the way the microwave clocks work that you're using, there's some microwave oscillator, quartz crystal usually, creating some radiation, say at 9 gigahertz, that atoms can absorb. So maybe that's a cesium atom or a rubidium atom. And then you can use that absorption signal to generate a servo loop and create the nice 10 megahertz that you want to use in your application. You don't have to know what's in the box. And this is what's, everything you can buy on the market is using this kind of technology. A lot of the newest microwave clocks have added lasers to either improve the Q, or say in the case of cesium, optically pumped cesium beams, they might be improving the signal to noise. And those factors really help with this clock instability formula you're seeing there on the upper right. In the case of, say, a MAC clock or a CSAT clock, they might use a laser to deliver the microwave radiation because it makes the device smaller, or lower power, or cheaper. And so these are all kind of, so laser technology being added to microwave clocks has shown to be pretty useful. But we're kind of talking about something different here, which is to truly use an optical frequency as the primary standard. So if you think about optical clocks, the diagram is a little bit different. The performance formula is basically the same, but now we're using a laser beam to do the spectroscopy on the sample. And so that might be at 500 terahertz instead of 9 gigahertz. And so then you can make a very stable laser. And because the frequency is so high, that Q factor can be really large. And you can improve the performance. The hard thing here is it took a Nobel Prize to figure out how to make that signal useful. So the advent of the frequency comb allows you to kind of compare the optical laser, provide 10 megahertz by using the frequency comb as an intermediary between the stabilized laser and the real world. And so this scheme has been very successful. You can find tons of papers where the optical clock performance is 100,000 times better than any microwave clock that you can buy. I call that one Colorado result there. It's one of the leading ones, the Bacon collaboration. And so this is sort of, in our community, this is known as a great way to do it. The hard part has been all these systems take a lot of lasers, vacuum chambers, cavities, and usually a postdoc army. If you look at the author list on that Nature paper, for example, there's a lot of people to get those systems working. So our approach has been a little bit different. We wanted to pick a system where you can get some of those benefits from operating at optical frequency, but the system can be simple and practical. And so we've been looking at developing these iodine clocks. And there's a lot to like about iodine. It kind of sounds strange to use a molecule instead of an atom for your clock, but actually for laser stabilization people, iodine has been around forever, and that's a common mature technique. And it was actually one of the first optical clocks on the Gilla system there, because it was sort of ready to go when the frequency comb came out. There's a lot of nice, there's still research going on for iodine clocks for space. There's a team in Germany doing really cool stuff. And also DARPA's had programs making very small iodine systems. So, it's kind of nice. You can use one platform for both applications. For us, when we were starting the company, the reason to go for it is we kind of saw you could actually get better performance than all the commercial products out there. So that's how you get in. And then the molecules, it turns out molecules are less sensitive to things like magnetic fields and temperature. So there's some advantages there. And of course, we try to keep the lasers as simple as possible. So there's nice green laser solutions out there. You can see that green laser there. So a little bit more about how you make a clock out of iodine. So on the left, you're seeing a view of what a spectrometer looks like. So there's a glass vapor cell containing the molecules, and then there's two laser beams opposing each other to generate a nice absorption signal. And this is a pretty nice system because you can bond everything down. There's no moving parts. You're measuring with high bandwidth and CW, and there's no atomic oven that can run out or anything like that. So it really checks a lot of boxes for real world use. Because you're doing absorption measurement, you get really nice SNR, and that's how we can get the good stability and phase noise specs. And then, we care a lot about protecting those molecules from the environment, but with iodine, you don't have to work quite as hard because you don't need multi-layer magnetic shielding or thermalized setup. And overall, if you look at the block diagram of the system on the right there, that's what one of our first clocks looks like if you open the hood. There's not too much going on, so you can you can fit all the stuff in one tidy box. You know, there's a frequency column, there's a green laser, and there's a little spectrometer and a couple of FPGA boards. So it's pretty simple system. And you know, from our perspective, we want to beat the maser on performance so that people adopt the optical technology. We want to match, you know, rack mount style clocks like cesium, and then we want to get it out in the field like rubidium clocks. So we've done that. I think a lot of people have seen this clock now at conferences and things. But so here's sort of the newest version of the iodine clock that we have here. Vector, Evergreen 30, Evergreen, Everlasting, all kinds of things there that you can work with. But I think the exciting thing is that we are now hitting performance levels better than masers on short time scales, and it does fit in that cesium form factor. And so there's some specs there. I won't go through it all, but the common questions are, you know, is the frequency common side? Yes, there's 10 megahertz and 100 megahertz outputs from this box. You don't have to know that there's lasers inside, but we do offer the lasers because a lot of the community actually wants to link up to the stable laser outputs as well. So that's cool. I think this is the first fully integrated system. It's turnkey. So again, the users don't have to be clock developers, and we're offering the best performance at short time scales that you can get commercially. So that's exciting. I'll talk about some of the uses we've been exploring. That'll be the meat of the talk. After kind of showing this off, we've gotten a lot of interest from the community. So we've been hustling to set up manufacturing. So we just moved to a larger building to kind of accommodate that in December, still in Pleasanton. And we've started setting up this manufacturing room. And there you can see a little pilot batch of the next units being built. So that's pretty exciting. Just real quick, I see if I can pull this off. I have one of these guys sitting next to me. See how my camera pointing is, running the labs, or running in Jamil's office here. So, you know, it's really just a simple box with a power cable and your outputs on the back and a touch screen. There's no, you know, supporting equipment surrounding it. So that's pretty exciting. If you haven't seen one, next time you're at one of the conferences or in town, I'd be happy to show you. Our approach for fitting all that optical technology in one box is highlighted a bit here. So the hard thing is that all these systems are new. You know, there's lasers to deal with, frequency comms, electronics, and spectroscopy. And so, you know, we've been working hard. We've been working hard to make a lot of this stuff in-house. For example, the vapor cell, you know, if we're selling a clock, the vapor cell needs to be controlled by us. The frequency comms a big subsystem, and there's integrated photonics in there that we design and package here. We have an awesome electronics team. And what's cool about this is now that, you know, in the newer versions, now that we control all the subsystems and have eliminated OEM modules, you know, the supply chain is a bit better. You can make it smaller and lower power and cheaper, and then you can do more with your system automation to get to turnkey. So that's been exciting. So enough about what's in that box. I really want to highlight some of the work our team's been doing to get these units out in the field and figure out, like, how do we get optical timekeeping to people? What are the use cases? Do we need some other outputs to expand to more use cases, things like that? So our team's been hustling for the past 2 years to kind of go around to different sites and see how people can take advantage of this new performance class. And you know, one example I'll talk about is using it in a time scale or as your primary reference in a facility. Maybe that's a data center, maybe that's NIST or USNO. We'll talk a bit about the use of those kinds of quality clocks, but on mobile platforms. So that's exciting. You know, we're finding we can get performance out on the move that you know, historically it's been chained down into a basement lab to get that kind of performance. And that also touches on over-reliance on GPS. If you can get these premium clocks out on ships and things, then you can solve some of those problems. Quantum computing, believe it or not, can really benefit from these systems. There's not a quantum computer in that box, but a lot of different hardware is being developed for quantum computing that requires either very stable microwaves or very low noise lasers, or simply just a ton of lasers locked to some optical reference. So there's some exciting things you can do in that area. And then, just the low noise nature of these optical systems, when you look at how the microwaves perform, it's pretty exciting. And we've gone and worked with partners at ARL to study that, which opened the door to some pretty exciting experiments where we've investigated how these clocks can help VLBI applications, astronomy and radar. And then finally, we want to get the clock to as many people as possible. And so you need good networks to distribute the signals. Not every building is going to buy one of these as much as I'd like them to. You need to distribute the timing around the world to really take advantage. So we've done a lot of work in that area. Before I get to that, some of the other demos we've done have been more to show that optical timekeeping can be real. So when we first got one of the systems fully turnkey, immediately all of our government sponsors came calling, wanting to show their bosses, and so we hit the road to Washington with one of the systems there. Check bag on United. That was probably the scariest part of the demo. But this is a situation where it's not scientists showing up and installing things and getting things working with laptops. It's us handing them the clock, and then they press the on button. And for a lot of the demonstrations that happened on that trip, we weren't on site. We were back in California, and so that was, those demos weren't to get good data, but I think really speak to the realness of this, and showing leadership at DARPA, ARL, and at this White House demo day, I think was pretty cool. Makes optical clocks really seem like real devices, and I think everyone's pretty excited about Eagle's trip to Washington. So in terms of using clocks, we've shown this a bit before, so I'll just show the overview, but we've taken multiple clocks to places like NIST and ran them for, say, a month against real time standard, the NIST AT system, which is comprised of maser ensembles and cesium, as well as more advanced clocks. And so the blue data shows how one of these nice iodine clocks Pickles did versus one of our clocks on a maser. And so what we see is the short-term instability outperforms all the masers and micro clocks they have at NIST. But what's really interesting is if you look at the gray dashed lines, which is the maser ensemble, and then what the iodine can do, people know you can get good short-term stability with these optical vapor cell systems, but the long-term stability proves to actually be fairly competitive with masers as well. So I think there's a play here as a primary time-based helper in an ensemble, and maybe if it's the only clock you have. The green line there is what cesium does. So anyone out there who uses cesium, the performance at short times is kind of off the chart here, but we can hold cesium for a pretty long time. The little black triangles there is when we remove the linear drift from the clock. And if you do that, which is easy to do in an ensemble, then you can stay below cesium for very long times and compete with the best masers. And exciting thing about this is that, we've seen that over time, the drift rate gets lower and lower for these clocks. And so we've got some new data that'll come out soon showing that, you probably don't need any drift removal to keep up with those best masers. We've also studied the newer generation clocks in this sort of what I would call national lab environment, where how well can they do as frequency standards in a pretty stable lab. So here the temperature control is really good, 1/4 degree, 1/2 degree, and you're seeing the eta between two iodine clocks. So short times we're below 3 × 10⁻⁴ per root tau. So that's the best thing you can get. And at long times, the stability is pretty good. So you can hold low 15s, 215 at a day. And the long-term drift, if you keep running, is pretty similar to the clock on the previous slide. So that's pretty exciting there. It gets real exciting if you look at smaller subsets to kind of see, where this can go. So if you only look at a 12-hour window in a stable temperature, then the clock makes it into the 16s, which for vapor cells is pretty challenging. The team's done an awesome job there, but that's a pretty exciting result. So I think generally, these clocks can play a role as the main clock in a facility or in time bases. If you want to look at it from the accumulating timing error perspective and how it compares to the other clocks used in time bases like cesium, masers, and even the GPS clocks. You can kind of see the timing error in the green dots for that clock. You know, it holds a 100 picosec now at 10 to the 5 seconds. And so that's staying well below a lot of these other clocks and can maybe enable some new applications. So that's pretty exciting. So switching gears, you know, can we get that same awesome performance that only these premium facilities get to use on moving platforms? Well, that was the topic of this paper that came out today. But just as a refresher, you know, we took 3 systems in 2022 to see how they did under a more real world environment. You know, getting great data in NIST is awesome, but trying to see how they work out in the real world with moving ships and magnetic fields and humidity, all this stuff, that's an important topic. So we went out to investigate that and ran a couple 3 clocks for a couple weeks alongside an atomic gravimeter that we also used to do navigation studies. And you can see the ship drove around the Hawaiian Islands, which is fun. And the kind of punchline is we can still hit this kind of 100 picosecond level timing error one day, even in this environment. So now you can think about having, you know, national lab type timing on your moving platform, which is pretty exciting. Here's a couple of data plots from the paper. So there's the timing error comparing on the left. That's the timing error compared to running at NIST with and without drift removal in the blue. And at C, we saw, you know, pretty much the same result at short time scales and long time scales. The data's on top of each other. And then you see some of the environmental systematics on medium time scales, you know, because the environment was changing by 3 degrees instead of a quarter degree. But generally, you can get the same premium optical quality result there. And then on the right is kind of an interesting plot John made, where we looked at some of the motion of the ship recorded by our gravimeter team, which is paying close attention to those details. And we saw sort of no noise coupled to any of the clocks at the frequencies where the ship's bobbing around and tilting. And that says a lot about vibration immunity, the orientation, magnetic fields, things like that. So that's pretty exciting. We've expanded our effort now to test how clocks can do in the real world. So we built a little dual clock system there on the left. So that's 2 fully integrated, you know, premium performance optical clocks in the little rack with a microwave phase meter and a counter to see how they do. And then we've started campaigns driving around California, where you know, we're driving around on city roads, highway, windy roads. Local folks might recognize the view from the top of Mount Diablo there. So that's a nice setup where we can do 3,500 foot elevation gain in like a 40-minute drive from home. So that's kind of a fun one to do. Other aficionados might notice that this is a premium 2005 4Runner. That's important to note. And so we're not, you know, there's not some special equipment in there. It's just strapped down and running with the battery. And so at a high level, what I can say is we're getting those same awesome short-term instability ADEVs while driving around doing these measurements. And we're working through the approval process. So Mike is probably going to be able to show some of those results at CLIO. So definitely go to his talk if you're there. Okay, so I think I've maybe convinced you that optical clocks can play a role in a facility, timescale, and you can take your timescale to go, which is exciting. But we need to reach further. And so, you know, we look here at a simplified view of how GPS works. You know, so there's your facility in the upper left, say at USNO. There's a bank of masers and cesium clocks, and there's some premium rubidium fountains that provide the best long-term stability. And that's great. So we can put iodine clocks there. But then to get us the rest of the world, right now there's 2-way RF links that go up to GPS satellites that also have microwave clocks. And so the issue there is that people have worked hard for a long time to get that to nanosecond, and we want to do picosecond. So it's not enough just to upgrade the clocks at USNO if we want that to distribute this worldwide. What do we need to do? Well, we do need to upgrade those clocks. So maybe there's a check mark there. We also need to distribute time precisely in facilities. There's existing good solutions using fiber techniques. But the part I want to talk about next is how to do the transfer over free space, how well you can do there. That's a big piece of the puzzle. And finally, the clocks in space also will become a limit once you solve the distribution problem. So there's sort of a couple more pieces of the puzzle before we can get the world to picoseconds. And so I wanted to highlight one of the cool ways people are working on this in our field, which is the NIST group. Laura Sinclair is leading this frequency comb-based effort to show how to transfer the very best clocks, even better than what we're showing here, over optical comms. And they recently did this experiment between 2 islands in Hawaii, which is just awesome, 300-kilometer link, and show that they can deal with the power losses and the turbulence and things like that. So that's really exciting. At Vector, we're collaborating with them to try and operationalize, miniaturize the optics part of the system, which is the frequency comms and the discriminator. And so we kind of see that as a good piece to make this sort of a real world device. And so here's a little bit of the work led by Armand's team here, which is we've made these rack systems that kind of look like the clocks. Each one of those boxes has 2 frequency comms in it and one of these photonic chips to make all the signals work out from the local and remote sites. And so those we've been testing at NIST's 15-kilometer link in a folded way. So sometimes we can do 30 kilometers, and we've tested them down to picowatt scale power. So that's kind of the power levels. If you want to go to space and back, you know, then you're getting the right power levels back to test the system. These pictures are a bit old. There's a newer, smaller system. So this is an active area that we're working on. But what was cool is taking that system out, we can now go back to our TDEV plot and see how that kind of system works. And so we have the same, all those clocks there plotted, which kind of start accumulating a lot of error as you go in time. But this optical sync method can hold 10 femtosecond stability. So we have a lot of headroom, which is great. You definitely want the distribution system to be better than the clocks, because the clocks are going to keep getting better. But we think this really shows a potential way to get to this worldwide distribution. So we showed that we measured clocks, we've showed that we've measured links, and the next obvious step is to combine the two. And so our team just got back from Boulder, where we took, this time we took clocks and those link systems and set up, in collaboration with Laura's group, a 3-node system. So you're seeing there's 3 sites that are sort of independently run. At the NIST side, site A and B each have a fully integrated clock, as well as comb and transfer setup to run separate links to that Table Mountain site. And then at the Table Mountain site, there's another clock and another set of combs that do the transfer. And so we're able to compare clocks around the loop. We're also able to compare clocks that are sitting right next to each other, so we can get some truth data, which is pretty useful. But this is really exciting to get out in the world and show, you know, all these things can go places and be used to make a network. So here's what some of the hardware looks like that we made for that demo and took out there. So this time we stacked up clocks and those sync modules all together for the NIST side. And for the Table Mountain side, we took one of the newer clocks and the newer smaller systems out there. It's easier to move those systems. And so there's a lot of details here. An important one is the battery backup system, which came in pretty handy. I'll talk about that. But the savant out there might be noticing that there's 9 frequency combs in this picture, and we really only need 7. But that's just the hardware we had. So there are some extra experiments we can do with extra frequency combs. Always good to have a couple extra. And so this one is another one where we just got back, and the results are coming soon. But it was pretty exciting, and I'd keep an eye out for this work. And there's the team there, Vector and NIST and Octosib came together to get this done. We picked the worst possible month to be in Boulder. There was a top 12 snowstorm of the past, 50 years. And so there may have been some skiing that had to happen to get out to that site to restore power. So some fun stories. In the end, we were able to get the three link nodes working together. So we're pretty pumped, and it showed it can support the iodine clocks being distributed around the loop. So we talked about clocks for keeping time, and then how to disseminate the time all optically. And I want to switch gears a little bit to talk about the other advanced properties of the clocks, which is this premium quality microwave noise that you get, microwave phase noise that you get by doing everything optically until the final stages. And so recently we were contacted by people at the Event Horizon Telescope, Dan Marone's group, and University of Arizona. They run a couple of the radio telescopes that are used for VLBI. So here you can see in the left picture how this works is a number of radio telescopes will point at the same object in the sky, and then you can get a large synthetic aperture if you can coherently combine the data streams from all those sites. And that's how they've gotten some of these incredible black hole images that are in popular news, things like that. So really cool technology. Also, similar stuff's done for radar or geophysical studies. And what these folks need is they're generating 200 gigahertz or so, but everything starts from the 10 megahertz output of the lowest noise measure they can get, or OCXO. They really care about short-term. They need the best short-term stability and phase noise that they can buy. They do want atomic aspects to it. They want to be able to align all the sites to better than GPS and have it stay for weeks so that they can combine the data later in post-processing. So you can't do it all optically. You need some atoms to steer as well.
Again.
And
Yes,
so, okay. So here's some pictures from the site that we went to. So we brought 2 of our iodine systems there to do some experiments. And we sort of started out thinking, well, we'll do some experiments with their team and learn how the systems work and collaborate and take some data. But it happened to overlap with the spring run. They do a couple runs a year where they can get all the telescopes pointing to the same things. And so, so we got some cool data versus one of these really high performance masers because they need the best, like I mentioned. But then we also were able to leave a clock running there for a couple of weeks so that they could plug it into their system. Some fun pictures here. You can see the swap argument, 2 iodine clocks and all of our measurement stuff. We were in basically a storage room where the maser and environmental chamber live. And so we had to use that as our table. There's no other place to put the clocks, but luckily those things are small and easy to move around. And so that's kind of the setup. Plenty of nice photos, but the kind of punchline is the data looked good. And so we were pleasantly surprised that they actually plugged it in. And so here's some cool astronomy stuff that I won't pretend to be an expert on, but the back end of the 2-week run, they decided to plug in an iodine clock there at peak, Dan's group did, and they were able to pull a little bit of early data from the 2 telescopes that they run in Arizona, which are on different mountains, but SMT and Kitt Peak. And SMT, there was a MHM maser. And they did this while studying this cool quasar that you can read their papers on, 3C279 there. That's not an image from our data run, but just a little bit about it. That's there's a black hole there, and there's this jet you can see moving away. And apparently that thing is going at 99% speed of light. So that's a very interesting object that their team's interested in studying. From our perspective, we were just thrilled that they saw this fringe here in the middle. So that's showing they're hunting the data sets between the 2 sites over time delay and rates. And then they saw this wonderful fringe. And what we gathered from them is this is a very good fringe. I don't know, honestly. But they record the amplitude and phase of the 2 sites. And they can make this plot on the right where they show a 4-minute window, and everyone was excited and started talking about how to get more clocks at different sites. So this is really cool. Maybe after they do all the data analysis, we'll see some images where optical clocks helped. It takes many months to actually create the images. But I'm pumped because in the previous section we were talking about reaching optical timing around the world, and so now I'm going to claim optical timing reached 5 billion light years. So that's pretty cool. A little of the fun data. I think it's really interesting to look at how the clocks do versus the maser. So again, this is really, there's all kinds of masers that have performance classes spanning a factor of 10. This is the lowest noise one that you can get. So that's why they're using it. And they really cared about 10 milliseconds to 100 seconds. So we don't usually take a lot of data there, but we looked at that. And so here's some measurements where the solid lines are showing raw data between iodine in blue, and iodine and one of the iodines on the maser in orange. The dashed line, we separately measured three-cornered hat and two iodine versus each other. They're very similar, so that's just a root 2 on the same data set to kind of show you where the iodine's landing. And so again, we already showed, the stability at a second is 3 or between 2 and 3. And it's actually interesting, for both devices, the 10 and 100 megahertz are slightly different. There's systems inside the boxes either dividing or multiplying to get to these different frequencies. So the details here go far beyond what's the 1 second stability. I think the upshot that we learned here is, iodine can beat the maser at both frequencies in this interesting band for VLBI. And if you're designing a new system, you might want to pick the 100 megahertz because then we're adding less electronic noise in our division circuit. The optical systems would prefer, they do the best if you provide a higher frequency. And so you can see the gap in performance is quite a bit better at 100 megahertz. So that's interesting. Another interesting observation, masers have this wonderful property of averaging down as 1/tau. So even if you tie with the maser at 1 second, it's creaming you at 100 seconds. So, we barely can hold on for 100 seconds, even though we're beating it at 1 second. But on the flip side of that, at the shorter time scales, the maser's kind of creeping way up. So there's a 10x advantage. So that's kind of interesting. Depends on what your region of interest is, how much that, what the impact of that 1/tau is. We measured phase noise as well. So, just direct head-to-head measurements. There's no root 2s or 3 dBs removed here. This is just raw data. But so you can see, we kind of expect a small win at 1 hertz. But there's some interesting structure where different applications might be able to take advantage. So at the 10 megahertz plot, there's a 10 dB advantage or more at the high frequencies for the phase noise. And on the 100 megahertz plot, the masers have this servo bump at 40 hertz. And so if that's in your measurement band, you can actually crush that down pretty well by switching to an optical system. So that's super, super exciting. Okay, so just a few other cool things we're working on. I mentioned clocks for the ground, how to transfer the clocks. We still need clocks that can get up in space if we want to take advantage of all this performance. And so here's some of the things we're working on. We got the full clock evergreen that I've already talked about, but we're working on 5-liter and 1-liter implementations of the same technology. So the 5-liter implementation, which is a DARPA project, that's pretty interesting for, say, a GPS satellite. It's the right size, and we're projecting hitting the same performance as the rack system with that. So you can really start dreaming up what you could do with that performance in space. And the smaller clock music, which is a project with ONR, that one we're pushing even more on the size, weight, and power, but we are relaxing performance. So maybe there's something interesting you can do in a CubeSat while still having sort of maser quality performance. And so, can iodine work in space? Well, there's a lot of space missions that have used components for iodine, and there's a big collaboration trying to field iodine on the ISS. So I think the answer is yes. And there's some interesting advantages that the molecules have. Things like magnetic fields really can hurt in space because you're orbiting the Earth. Things like helium collisions can hurt as well. And those things are small for iodine. So that's pretty exciting. And it's more than just CAD. So we're building real hardware for these things. So here's a little spectroscopy unit we made that's a 10th of the size of the one in the rack system. The data's still good. We're in the low to mid 13s typically with this at 1 second, and we can still get down to this premium performance at long time scales. So I think this is really going to happen and be an available technology. The other thing we're working on in the group is, replacing the ultra high accuracy clocks where there's not very many of them out in the world, but they anchor the backbone of those timing systems, whether it's rubidium fountains or optical clocks. And so we have a strontium project here that we've been working on. This is more in the R&D phase, but I think the technology is maturing to pretty interesting levels, both on the atomic package and optics. And so here's a photo of a liter scale system that we recently made and brought to NIST for evaluation. And then there's this middle picture. For those unused to seeing these things, this is a ball of 1 million strontium atoms trapped by lasers and glowing. And then on the right, what you're seeing is there's this complicated pulse sequence where the atoms are collected, trapped, and ultimately loaded in this optical lattice. And that's how you get those clocks that are 1 million times better than the microwave clocks. So this is not a full clock that's a liter, but we've kind of made one of the hardest parts really small. So now it's getting interesting. Can you put this in a maser-sized clock, but something that has a few orders of magnitude better performance than a maser? So I'm excited about that. And with that, you can start dreaming up, maybe with all these things I've shown, you really can start dreaming up a real interesting worldwide optical system. I'm not an expert in this, but I can point to the master clock room at USNO and say, okay, stack up 10 iodine clocks there. We can say, okay, add strontium to that rubidium fountain room. In fact, they're working on that as well at USNO. And so then we can get the on the ground timescales to where they need to be. And then I think we've shown that there's paths to make the optical links make it to space with frequency comms. There's other techniques people are working on that are interesting. And so we can get the signal up into space. And then these small clocks that I mentioned give a path to make networks of satellites that have either the full performance in a 5-liter package or something smaller where you can make a swarm of CubeSats or something like that. And so I think there's probably a lot of people who have more expertise in how you would make this system, but I just wanted to convey the building blocks are starting to come online and they're in the pipeline. So it's good to start thinking about it. Definitely want to thank the Vector team for doing all these demos. It's hard work. Looks like a little typo there, but we used to say join Vector Atomics, see the world. That's supposed to be deleted to say universe. Now that we can go 5 billion years, people are dreaming up what stars look like. But here's just some fun pictures of the crew going off to all these demos. I counted up this morning that there's something like 30 installs now of clocks and sync modules for all the largely for our government projects and in studying commercial use cases. And so 30 different times one of those white boxes went out and got installed somewhere and used. And part of the reason that number is so high is because the clock people know you can never bring one clock anywhere or the measurement is not very interesting. And so a lot of times we're bringing 2 or 3 systems or that 3-node thing with 6 systems that we have brought out to Colorado. So we're learning how to get the stuff out in the world. And these are the guys and team getting it done, plus the whole team back home who design the system and develop it. So definitely want to acknowledge these folks. And for those of you on the line who might have asked for a demo, you can maybe understand why sometimes we're like, maybe in a couple months because there's a queue and we're trying to hit everyone. We're definitely interested in doing a lot more demos to learn how these things can be used, but we've been pretty busy with it. So finally, for acknowledgements, the sponsors, of course, a lot of Army, DARPA, and Navy projects helped to get us where we are today. But for these, this is a talk about field demos, and every single one of those demos had people who were there with something to plug in or measure. And so for the clocks at sea, Tommy's team at ONR, as well as AFRL organized that. We were hosted by this crew on the Navy ship, New Zealand ship. On the optical time transfer experiments, that's been a long-term collaboration with the NIST team there run by Laura. And so that definitely want to acknowledge them. For the timescale measurements, working with Jeff Sherman, as well as the optical time transfer team at NIST. For this hot news of the VLBI, that slide just came to my desk a couple days ago. I want to thank Dan Moran, who made it happen and convinced his colleagues to point the telescope doing their precious run with our clock. It's pretty exciting. Laura Sinclair is involved in that as well. For the microwaves, I didn't highlight it here, but we did the kind of step before the VLBI experiment was to characterize all those systems, which we did with James at ARL. And then our sponsors help us a lot to make progress, but also literally did some demos for us with EG30 Goes to Washington, as well as Gretchen Campbell from the White House team. So these folks went and I think had fun putting optical clocks in their trunk and turning them on places to show their larger community. And for the Strontium setup that I showed, that's been a collaboration with Scott Papp's group at CU and NIST and Mit's group, who made I didn't talk much about it, but part of the trick there is to make the optics delivery really small with integrated photonics. So happy to ask any questions. Let me know.
Wonderful. So thank you very much for this amazing presentation. Learned a lot of details of like what we can do potentially with the iodine clock. So there was a question from the audience about can you sell to Europe?
Sure. There's no real barrier on that. The device is going to be EAR protected in the same way that a Maser is. And then we're working through those details now, hoping I'm hoping that we can kind of start doing that by the end of the year, if not early next year. But I think, we definitely want to do that. And there's not a ITAR barrier necessarily, but there are export control paperwork that we need to go through and RoHS and things like that. So there's sort of work to do, but we absolutely plan on, having these in Europe.
Wonderful.
Mm-hmm.
So let's see. We open the floor for questions. Please, now you can unmute and ask your question.
I have a question that you might not want to answer, but how much does the clock cost these days?
I'll be happy to give you a quote if you email our sales team, Julie.
Okay, and
I can
how
say,
many?
I can say, it's that's a moving number, but it is. Let me see if I can go back here.
Marty is pulling the calculator, right?
So, it's cheaper than this and better than this. So I think we have a good starting point. Our goal is to get it down close to cesium. The first units are going to be more because we're kind of building up the team to do that. But these Masers are 500K or something, and so yeah. even unit first units are below that, and then we're on a slope now to kind of get big factors.
And how many units have you guys built at this point?
We've built I'll answer on the government side for the the things captured here was six units for the clocks and 4 units for the sync modules. Went out and did all these demos. So that's for the government contract part, which I can answer.
Cool.
And how far are we from having like something like this, Marty?
Well, how big is that?
I mean, this is a 2x2, I think. Yeah, like, I mean, we call it the LOF, LOF, right?
So, for what our team has done, we've been focusing on something that's a liter, which is maybe a little bit bigger than that, but not too crazy. So that would fit in a VPX chassis slot. Certainly, like the vapor cells and the lasers, a lot of people have shown that you can make them on a chip, and we're working in that area using integrated photonics. Those are still on the R&D, so it might be 5 years before you'll have something that's really using all chip scale lasers.
5 years. All right.
Yeah.
Any more questions?
Could I ask another question?
Sure, go ahead, Judy.
You guys did some de-drifting. You got some awesome data where you didn't even need de-drifting. What was the linear de-drifting though that came out of the 35-day test at NIST?
So that you can find in the paper. Let me do this more efficiently here. I might be off by a small factor of shooting from the hip. Let me see if I have that plot. Here we go. So this slope is around 10 to the minus 20 per second. And then linear removal is a factor of 10. And then I don't want to spoil John's talk for Cleo, but it's a pretty big burden, which is largely the cell settling. So I mean, we're working hard to learn how to do that out of the box.
And are you guys using those really tiny cells that you had the nice Leo picture with?
It depends on the box. Yeah, it's
Okay.
it's a variety. Yeah. You know, let's see. Oops. Here's a picture of some cells. They're not the same in each box. You know, the different platforms we're developing have different cells and optics and things like that. We aren't using the one that was in that picture from Leo's finger. We made our own small cell that has some different windows and things. That's sort of in our secret sauce, but yeah. Making
This is
them
really cool.
Yeah.
Yeah, thank you guys so much. This is awesome to see, and it makes me so happy that, you know, there's a whole community of people working on optical clocks and getting better timing out there. It's awesome.
Wonderful.
Sure. Happy to show it off.
All right. Any more questions? All right, so hearing none, we'll just go with also announcing the next OCP tap call, which will be the 100th call. And we'll have like a special event where we're going to have a fireside chat with the inventors of PTP. So we look forward to see all of you there and ask those who started PTP, how were things at that time, and what made them to dare to do such big things, and we'll have fun all. So again, thank you very much, Marty, for this great presentation. And as always, the presentation is recorded and will be on the wiki alongside with the slides. All right.
Okay, thanks for having me. It was fun.
All right, see you guys in 2 weeks. Oh, and I mean, just not forget, in a week, we're going to have basically the meeting, the kickoff meeting for a new work stream, which Hisham and Dan are leading. Dan, is there anything else like you want to also add before we close the call?
No, basically on the chat, I just put, we've got a draft of the work stream up on the wiki. So
Wonderful.
it's number 10, you know, people can go out and look at that and get an idea about what our initial plans are and stuff like that and the thoughts. And yeah, next week, you know, we'll kick it off and see how things go.
Yes, wonderful. All right. See everyone in a week or in 2 weeks. Bye, everyone.
Bye-bye.
Thank you.